Hi, we are Group 22.
Hi, I'm Brian Barrow, and with Group 22 we were tasked with testing the powertrain for the Oregon State Electric Formula Race vehicle. And this is the first year that this car was attempted, so we had some pathfinding to do.
Hi, my name is Mohammed Al-Afraj. We used the facilities of the Wallace Energy Lab as best we could. For logistical reasons, we were not able to test the motor at full power.
Hi, my name is Amar Al-Haji. In this video, we will review the motor controller, the motor, and the battery simulator.
I'm John Modre, and we will conclude this video with a discussion of what future teams will need to take into consideration in order to do high power tests in the Wallace Lab.
And I'm going to talk about the RMS motor controller and a unit that we use that was called a Motec ACL data logging unit, which is going to be shown in a slide here. And what these two components do is deliver power from the inverter circuit, which you've just seen, to the RMS motor controller, which takes in 400 volts DC nominally and outputs 3-phase AC to the motor. There's several configuration parameters that we had to consider as far as the motor controller was concerned, as far as being able to do a mechanical as well as a electrical phase matching in order to be able to make sure that the resolver, which shows your motor position, agrees with where the motor actually is and can communicate that information from the motor to the motor controller. So the RMS motor controller has several parameters configured, and it can operate in two manners. It can either operate in something called a vehicle state machine mode, where it actually receives input from a brake pedal and an accelerator pedal, or it can also operate over something known as a CAN bus, and that's the way that we implemented it. We implemented a product called the Motec ACL unit, which is used as a data logger and also as a control unit. And this control unit then sends simply just a torque command from that command unit, a commanded torque to our motor controller. And now Ahmed will be talking about the motor and the motor controller setup.
This is an overview of the block diagram. At the top you can see the RMS motor controller, which connects to the REMI motor, and then our test rig at the bottom with the torque transducer and the Wallace Lab dyno. You can see the input from the rectifier circuit on the left hand side and the Motec controller on the right hand side.
As you can see here from the picture, the motor controller is power the motor with 3-phase AC power, and this is the point, and this is from the motor. And the motor controller uses high frequency pulse width modulator. As we can, the welding cable which connect the motor with the motor controller can be potentially become broadcasting antenna of RF noise. The noise can interfere with analog and digital vehicle data, such as the motor resolver and temperature information. So in order to combat this, we use the cable, as you can see, is shielded with aluminum foil. Additionally, the cable shield is grounded to the motor chassis. So these cable, and right now we will show you some video of test bench for the motor with all components working together.
Here's the motor testing rack. On the left side, the green box is the dynamometer. In the middle is a torque transducer. And on the right is the motor itself. You can see black cooling hoses, silver AC power lines, and the green grounding wire.
And talking about the electrical aspects of the battery simulator. The actual e-car energy source is batteries. The batteries send DC power nominally at 320 volts to the motor controller. The Wallace Lab did not have that DC capability, so a passive rectifier was designed to simulate battery voltage. And here is the rectifier circuit. The rectifier will take line-to-line three-phase AC and rectify it to DC. It will produce a 360 Hz ripple voltage that will increase as more power is used by the motor. In order to smooth out the ripple, a 450 volt 10 millifarad capacitor is parallel to the load. For lab safety, the capacitor is bridged with resistor that discharge with an 8-minute time constant. All the principal load carrying wire is number 2 welding cables. There is a 110 amp fuse on the DC side for protection. And now, John will talk about the thermal consideration of the rectifier.
Of the thermal power that the diode rectifier needs to dissipate is proportional to the DC current running through it.
0.
The diode pack is tightly secured to the vaned aluminum heatsink with these 2 screws. This white thermal paste was used to eliminate any microscopic bubbles that are between the diode and the heatsink. This is a wire that senses the temperature of the diode case. Underneath is an 80 cubic feet per minute 12 volt CPU style fan that blows directly against the diode pack, and the air flows out of the ends of the aluminum heatsink. The Wallace Lab is ideal for AC, high torque, and low RPM motor testing. Say 2,000 Newton meters and 1,500 RPM. In contrast, the REMI motor can be characterized by 200 Newton meters and 4,000 RPM. Although the motor itself uses 3-phase AC, the actual vehicle system is DC battery powered. So future teams will have 2 areas to consider: battery simulator design and dynamometer configuration. Adequate cooling of the diode bridge in the heatsink is a necessity, not a luxury. Ideally, temperature should be sensed in the junction between the diode pack and the aluminum heatsink. This can be done by scribing out some of the aluminum heatsink in order to put a wire underneath the diode pack. Kathy Hahn, a graduate student in chemical engineering, determined that for a low power test we need about 80 cubic feet a minute of air blowing over it. She also determined that for higher power tests we actually need liquid cooling of the aluminum heatsink. The core of the battery simulator was a 100 amp rectifier. However, for 50 kilowatt tests, a 200 amp rectifier would be more appropriate. So we are leaving to next year's team 2 200 amp fuses that can be used to protect that 200 amp rectifier. Also, next year's team needs to know that Wallace Lab limitations are 175 amps DC. This is the Wallace Lab 300 horsepower dynamometer. It's nameplated to 2,450 RPM. Dr. Van Juan has suggested that under some circumstances it can be raised to 4,000 RPM. But no matter what's mounted to this dynamometer, it must have mechanical integrity. I hope that next year's team gets the same type of wonderful support from the Wallace Lab staff that we got. In fact, all activities in the Wallace Lab must be done under their supervision. I hope next year's team has a great time doing this, and thanks.